Hello and welcome to the Bentley Offshore Coffee Corner. My name's Jeff McDonald and we'll be talking about dynamic extreme wind analyses today. But before we get started, I wanted to talk about On24 a little bit, the platform we're watching this webinar in. If you're not familiar with it, you're going to notice a few buttons down at the bottom. I want to point out the media player and the slides. I'll be doing the introduction on the slides, but then we'll be sharing my screen, which will appear on the media player for the main body of the presentation. If you have any questions, you can click the Q&A button and type your questions in there. We'll address those questions at the end of the presentation. And if you are interested in me or any other Bentley related content, you can check out the speaker bio or the related content buttons. There are a lot of other great coffee corners that Bentley offers throughout the year, and I'd specifically like to point out the STAD, AutoPipe, and Geotechnical Analysis coffee corners as great supplements to this coffee corner. We have a lot of integrations with those products and a lot of interesting information that you or your colleagues might find in those as well. And if you need a continuing education credit for your certification, you can go to learn.bentley.com/transcript to download a copy of that. And we'd love to hear what you think about our coffee corners. If you have some ideas to make this better, just want to say that you're having a great time. You can submit a survey using the pink button at the bottom. And let us know how you feel. We'd love to hear about that. All right, with all that out of the way, I can get started on talking about dynamic extreme spectral wind. Bear with me for a moment while I get my screen up, and we can start talking about dynamic extreme spectral wind. All right, so most of us are probably familiar with the very basic static wind analysis where you define a wind speed and typically define some sort of wind height variation function, which just controls the wind speed at different elevations. And then what we do is we use Morrison's equation to calculate the forces on the elements, and there you go. You've got your wind analysis. This works pretty well for what we would call short environments, less than an hour duration, where the wind speed doesn't vary much. But when you start talking about dynamic analyses, we start to look at different factors that affect the response, particularly gusts, which can change changes in the wind speed, and also it becomes more important to look at variations in the wind over different lengths. So I'm going to talk about what are the differences primarily when we start talking about dynamic wind analyses and why those differences are there. After this, we'll go into an example to walk through how to define all this information. But just as a high-level overview, when we talk about doing a dynamic extreme wind analysis, we, of course, since we're doing a dynamic analysis, we need to extract our mode shapes. So we can do the modal analysis in DynPack. We're then going to calculate aerodynamic and spatial coefficients. These are going to modify our wind spectrum at different points on the structure. And then we can calculate a generalized force spectrum, which can be used to, as any force spectrum, used to calculate the dynamic response of the structure. We're going to calculate some transfer functions, mechanical transfer functions, that will then, you can calculate the response spectrum from those generalized forces, and we can use that to calculate an RMS response, a root mean squared response with a zero crossing period. And from that, we can do a complete quadratic combination of the modal responses and then calculate the total dynamic response. Okay, so if you've watched any of the other presentations on some of our dynamic analyses, some of these terms should be very familiar to you. It's a pretty straightforward if you're familiar with like a spectral wave analysis or anything like that. But there are some nuances to it, so I'll point those out as we go through. I'm not going to talk about modal analyses. I think that's a topic in and of itself. If you're interested, of course, we have some documentation on that. I'm not sure if we have any videos on it, so maybe that's a good topic to get into at another point. But I'm assuming that you know what a modal analysis is, what eigenvectors and eigenvalues are, and how to calculate all those. So I'm going to jump more into the spectral wind analysis. So here we can see the first thing is our wind spectrum. This defines a wind speed versus frequency. And we have three wind spectra that are available to us for dynamic analyses. We have the Harris, von Karman, and Freya spectrum. You can read more about these in, say, like DNV, RPC 205, when they should be applied. But I've just put the equations up here so you can see these. And this just really defining the wind environment, right? So this is how we are defining the environment, how the wind speed varies versus frequency. Okay, so if you're thinking in spectral wave analyses, this would be similar to your Pearson-Muskovitz spectrum, right? Oh, I apologize, I'm on the wrong screen. There we go. Okay, so here's where we start to differ a little bit. Here we have this JAI parameter that we're calculating here. This essentially is a wind height variation function that we are applying to the wind spectrum. Okay, so at the very top, that formula should look somewhat familiar. It's just the reference velocity and then multiplying the natural log of the elevation over the reference elevation for that wind speed. So this is just the wind varying over a height. There's another gamma parameter down here, which is the wind speed times some parameters. These are properties of the element. And you can see that we have a mu parameter, which is the mode shape. So this is just a parameter that accounts for the variation in the dynamic response of the element. And these, I should note that the I here is an element iterator. So we're calculating these things on an element by element basis. So the reason I've shown this, I've showed the same wind height variation here. This is really more the top term where we have the wind height variation, and the second terms down at the bottom are more of the element-specific parameters. Oh, excuse me, went the wrong way. Okay, so then we also have a spatial coherence function. Here you can see that we've got the JRI is our final output here, but up above that we have a coherence function. And this is just saying that this is dependent upon the frequency and the distance R, and that's the distance between 2 points on the structure. And all this is saying is that the closer 2 points on the structure are to each other, the um, the more likely that the two wind speeds on those 2 points on the structure are going to be the same. I've graphed the spatial coherence function, the top term, up there for you so you can kind of visualize how that works. So you can see it drops off a bit after you go away from that 0 distance point. And again, we have the gamma parameter, which is again just the CDB times mu I, which is the properties of the element itself and the mode shape. So we're calculating that spatial coherence function and modifying it on an element by element basis. Okay. So all of that together, the wind height variation function, the spatial coherence function, and the wind spectra go into calculating the overall wind spectra. Right here, I'm showing the term for the generalized force as opposed to the velocity spectrum. But as we talked about, that's just the Morson's equation, right? So we've just said, okay, these are the velocities over the elements, and we're going to have a force on the element that's proportional to these parameters, right? Okay, so this is our generalized force spectrum. Okay. And here we have a view of that chart. Okay, so we have on our converted our wind spectrum into a generalized force spectrum. We're going to do this for each mode. I think I might have misspoke earlier and I said that was an element per element basis. I believe, sorry, that was a mode per mode basis. I is in modal iterator. So apologize for that. Okay, so we've got our generalized force spectrum. So that was, I think, step 3 in our steps. Now we need to go to calculating a transfer function in order to get a response spectrum. So we have a generalized forces. Our transfer function is based upon a harmonic response to the wind speed, right? So we have this transfer function here. This is just the generalized stiffness of this mode, and we are using the damping to give us a this mechanical transfer function here. Okay, so this is similar to how we would do transfer functions for spectral wave analyses, where we run a wave through the structure and at different frequencies and plot a transfer function for the points, the responses to each one of those waves. But here we're assuming that we're going to have a harmonic response. So the transfer function we can just plot using this function here. Okay, so as we do in spectral wave analyses, or tow fatigue analyses or anything that's frequency domain, we can get the response spectrum by multiplying the force spectrum, generalized force spectrum, by the transfer function squared. Okay, so here we can multiply those together. And if you look, I don't know if I have a good way to go back through. I guess I can jump back to, so if you look at this plot, the generalized force spectrum, and kind of imagine yourself multiplying it by the mechanical transfer function, you can begin to picture how this response spectrum is being constructed, right? We see a little bit of a pickup on the left-hand side to account for the generalized force spectrum, and you see the harmonic excitation from the mechanical transfer function. Okay. And then we can, for each one of the modes, we've got a response spectrum. So in order to get the overall response, really the RMS response, this is the kind of the variation in the response, we can do the RMS RMS response calculation. So here we've got the square root of the integral of the response spectrum, right? Transfer function times spectrum by integrated over frequency. And down here I've got the CQC combination. So once we have the RMS response for each mode, we can go through and calculate the complete quadratic combination of those modes. Okay, so here I've got the formula for the modal correlation coefficients, right? So really all this is saying is if you have modes that are close together, and I've kind of shown that on the right-hand side here, then they are correlated, and there's a correlation coefficient. So we'll couple the responses of those. As you can see in the bottom formula there, sigma j total is PIK, that's the modal correlation coefficient, and then we iterate over the responses for the modes. If you kind of picture the modes as a 2x2 matrix, then you'll have a correlation coefficient for each pair of modes. And if there are no correlations, then you would just have a identity matrix, one, right? So this is just trying to capture that effect. If you didn't have any correlation, then you could just do sum of the root squares of the responses. Okay, so this is like, we do this a similar thing when we're doing fatigue analyses. You see the RMS response. So we're just doing this again, trying to get the variance and the total response of the wind for this environment, right? So this should look fairly familiar, but then once we get to this, we're typically looking at the average response, right? And we're assuming a Gaussian distribution, but we want to get the peak extreme responses. So we want to modify this response to try and capture the extreme, that's why we call it the extreme wind analysis, the extreme response of the structure. So we have a little bit more work to do down here, and this is where we, oops, excuse me, my PowerPoint just decided to escape out. There we go. So we have a little bit more work to do. We have to calculate, let me get that off there, excuse me. We have to calculate the extreme response, right? So I've shown this here. So if we assume a Gaussian response, the distribution of the extreme values are starting at this sigma square root 2 log, natural log Vt. This V is the velocity and T is the, oh, I didn't put T in here. T is the period, I believe. Yeah, so it's just the inverse of the frequency. That's right, the zero crossing frequency. Apologies for not putting that term in there, but yes, so that's the period. And so then we have a distribution of peak values, essentially peak values that are over that value. And then the average of those is that additional term over there, square root of 1 over square root of 2 log natural log of ET. So what we're trying to do here with this gust factor, this GJ term here, is to calculate the average peak value that's above this distribution. This essentially is saying we're going to capture the top 95 percentile of winds and say that these are going to be the extreme wind speeds. This all comes out of Rice's mathematical analysis of random noise. And we can calculate the dynamic amplification factor by taking that gust factor and multiplying it by that sigma j total and dividing that by the static wind force, right? So we can then just do a little bit of manipulation of the formula to give us the maximum force is equal to that dynamic amplification factor we've calculated times the static force. Okay, so that's how we're calculating the extreme wind. Essentially, at the end of the day, we're taking the wind spectra, we're accounting for variation in height and also variation in space, and we're also we're calculating a mechanical transfer function, calculating the response spectrum, and then from that response spectrum doing complete quadratic combination of the modes, and then we're doing some additional statistical analysis on the distribution to produce an extreme wind response.